Hi, my name is Daniel Chifo, and I was lead for building the robot, and I also helped with the code.
Hi, my name is Susie Cox, and I'm an engineering student at The Ohio State University. For this project, I was the lead on the wiring for the robot and assisted with documentation.
Hi, my name is Tori Vanderputten, and I was the lead on documentation and assisted in wiring.
Hi, my name is Josh Eason, and I was the lead coder for the robot project, and we're Milkshake 4.
In this presentation, we will go through the process Team M4 went through to complete this project. We will begin by discussing the robot mechanics and then move into the code that was written for the team's robot. Next, we will go over the budget and time spent on the project. We will then discuss future development plans and the additional resources needed for the plans. And lastly, we will end the presentation with conclusions about the robot project, as well as talk of more future development.
For the front wheels of our drivetrain, we had two Iguan motors, which were attached to the chassis with 3D printed mounts. And the Iguan motors were attached to 2.5-inch Dubro wheels with adapters. These Iguan motors have encoders built in, so we were able to know how far the robot was traveling as it completed the course. For the back wheels of our drivetrain, we also used 2.5-inch Dubro wheels. To attach these wheels to the chassis, we used 4 brackets, which would hold an axle. And then we also used 8 shaft lock collars to keep the wheels in place so they did not slip in and out of the brackets. Additionally, our robot had some trouble getting over the ramp in the course, so we had to add rubber bands on the front wheels so there's more traction on the wheels. For the chassis of a robot, we used a 1 square foot piece of 1/4-inch MDF. We used 3 layers on the base of our robot, and then we were able to repurpose the rest of the material in other aspects of the robot, like in our rack and pinion mechanism, which we weren't able to implement yet, as well as our sidearm mechanism and our holder for our QR code. So none of the material went to waste. On our robot, we added a sidearm mechanism, which was a servo with an aluminum sheet that could go up and down. This mechanism was used for flipping the ice cream lever, inserting the tray into the sink, as well as flipping the burger. In this mechanism, we used a high torque Phytech servo motor, which was then attached to this aluminum lever with epoxy. Next up, Josh will talk to you guys about the code that was used in the Proteus that was used to power all of the motors and tell the motors what to do at what times.
The code. The code was abstracted into different classes, and each class was housed in a separate file. This improved the readability and maneuverability of our code through various naming conventions and by splitting the classes up based on their uses on the robot. It also made it easier for other people to work on it when someone was gone. We made it modular through the use of functions. The FEH library functions were composed into larger functions or made easier to read by renaming them. Functions like moving forward or turning were made easier by combining moving the left and the right motors into the same function, with the parameters being the ones to manipulate the way the robot would move. We imported the classes into the main.cpp file. To keep main clean, we imported the various classes using #include and called the functions housed in the classes in the main file as needed. We also calculated useful constants. Useful constants like the encoder count for 90 degrees, converting encoder counts to inches, the servo max and min, and the motor voltages. These values were obtained through trial and error, math, and the various calibrating functions. Lastly, we used a shared Google Drive folder to share the code and to have multiple local copies of the current version of the code with each person. Next, Tori will discuss the budget.
At the beginning of the project, our team was designated $160 to use to buy materials and pay for services like 3D printing. As shown on this slide, we used $124.41 and had $35.59 left over. The graph created by the FEH store shows when we spent our money over the course of the project. Our first purchase was about half of our budget, but that's mostly because we bought 2 Iguan motors, which were $25 each, and we had to buy materials for the chassis. After that, most of our purchases were quite small. On this page is a representation of how the $124.41 was spent per category, including drivetrain, chassis, wires, and more. As you can see, the drivetrain is the most expensive part of the robot, which is reasonable considering that the robot could not move around the course without it. The variation in percentages is actually pretty good considering that the materials ranged in cost from 2 cents to $25. Here's a small section of our team's budget log in which we kept track of all of our purchases. Although the FEH store keeps track for every team, we wanted to stay organized and make sure no money went to waste by also keeping our own log. This is from the beginning of the project, but it is the same throughout. We listed the part, the quantity, the unit and total prices, the date on which we ordered the part, the category, and our remaining balance. It was useful when we discussed new ideas because we could consider what we have already bought and what we may need to buy. The pie chart on this slide represents the amount of time spent on each aspect of the project: documentation, coding, testing, brainstorming, construction, and exploration. In total, our team has spent about 128 hours on the project, in and out of class. Split between categories is pretty even, which makes sense because of the various assignments and tasks that fall into each of the aspects. Construction took up slightly more time than the rest of the categories, but that is mostly because actually constructing the robot was sometimes tedious and needed to be given some extra time. In order to get the data presented on the previous slide, Susie created a meeting log for every time the team worked on the project in or out of class. The log on this slide is from our in-class meeting on February 26, 2020. As you can see, we have a column for time, task, and contributors so that we knew exactly what was done each day, how long it took, and who worked on it. This was beneficial in updating our design schedule and keeping track of progress on the project. Next, Dan will talk about the future developments for this project.
For future development of our robot, we would have implemented our rack and pinion mechanism, which would have been used in pushing the jukebox buttons and sliding the ticket. Additionally, we would have used a larger chassis, which would have prevented overcrowding of our mechanisms on our robot, and this also would have helped with weight distribution because we had some issues where our robot was front heavy, and after going up the ramp, it would tip forwards a little bit. Additionally, with more room, we could have added bump switches, which could have been used for knowing when the robot was at a wall. And also, with a larger chassis, we could have spread out the wheels more, which would have left more room for a line following kit, which we could have used for the ice cream task and also pushing the jukebox buttons. Next up, Susie will talk about additional resources that we could have used in the building of our robot.
In order to complete the developments that Dan discussed, we would need the following additional resources. Most importantly, we would need more time for the project. We also would need access to power tools and glue in order to cut and attach things to the robot. To create a larger chassis, we would need more MDF to add to the robot, or if weight distribution was still an issue, we could have used a heavier material. We had one bump switch that we did not add to the robot, but if we were to add bump switches on the front edge, as Dan mentioned, we would need to purchase an additional bump switch. Additionally, we could have used a larger budget in order to purchase these items or more if we thought of them, and it would allow us to have enough money to replace something if it were to break. Next, Josh will talk about conclusions for the project.
In conclusion, the robot was built correctly and worked well, but there were aspects that the team would have done differently, if given the chance to do again. At the start, the team should have gone ahead on the building schedule. If this was done, the temporary parts we had to make would not have been needed. The code was done well, but there are areas that could have been improved. Some of the constants that were calculated were not recalculated to account for changes done to the robot. This would have made coding much faster. The budget was properly rationed. The time spent by each team member on the project was relatively equal, and the tasks were distributed well. And most importantly, the team got along really well and had fun.
Overall, for future development of our robot, we would have added a rack and pinion mechanism, and we would have used a larger chassis, which would have allowed the weight to be distributed better on our robot. And this also would have allowed for more features to be added to the robot, which would lead to better navigation and more success for the robot on the course. Everything else on the robot would have been kept the same. Thank you for watching.